In this video, we're going to continue our work in section 14.3 and look further at this idea of a differential that we met in the previous video. So what we saw in the previous video was conceptually how we can represent approximate changes in the output of a function if x and y change by a certain amount, dx and dy. So just notice here in that example, we were considering that the change in our function in the x direction and the y direction was constant throughout. That's not going to always be the case. As we vary in the x direction, we might vary in how much our temperature changes or whatever our output is changes. So this differential does give us an approximate change of the output of f. So in example 3, we're given to the right a graph of a surface and its tangent plane at a point AB. And that's the plane that contains the point S. Or rather, here, there we go. So we have a point on our tangent plane, and that's a tangent plane at the point AB. And we want to find the z coordinates of R, S, and T. So notice where R is, S is, and T is. And use them to find formulas for df and change of f. So before getting into that, I want to first scroll down a little bit and look at some of this notation. So here we have changes in the function z equals f of xy. And so conceptually, we have some notation here. So delta x change of f, or delta f change of f is going to be the exact change in f between the point AB and a plus change of x and b plus a change of y. So that's exactly the change of the function, while df, the differential, is the approximate change of f between the points a and then a plus a little bit and b plus a little bit. So we have an exact versus an approximate change. So then just using this picture to help sort of guide what is going on here. So rather than carry out the derivations in example 3, I want us just to talk through this diagram and come up with those formulas for the change of f, the exact change, and the differential or approximate change of f. So what we're considering here in this diagram is looking at the point AB. Then we see the output of AB of our function is AB, f of AB. And we see that's here on this surface of our function f. Okay, so then now let's consider the point a plus some change of x and b plus some change of y. So here we're going to move delta x or dx in the x direction and some change or delta y in the y direction to get to a point P. So notice at P, our output is up here with the point labeled T. So here, this change in f from our starting point to T, just this vertical change or the output change, is that delta f. So how would we represent that using a formula? Well, what we're going to do is just compute the output value at our point A plus delta x and B plus delta y, and then compare that to our first input value. So that would just look like f of A plus change of x, B plus change of y. So that's the output at this P input value. And then we subtract that from the output at the value f of AB. So then now let's consider that approximate change of f, or the differential df. So we can see that we calculate it from the previous example. We compute partial with respect to x at AB times the change of x plus the partial with respect to y at AB times the change of y. So we can see what's happening there graphically. So what we're essentially doing is looking at where the point is on our tangent plane above the point P. So I'm going to go ahead and outline that tangent plane in red. So here's our tangent plane. All right, and so that change, that slope in the direction of x times the change of x is going to put us up to this point. And then the change in the direction of y times how much y we're moving, or in the y direction, will take us up to this S point. So then the difference between S and T, this difference here, it's a little mislabeled on our graph, df, tells us that approximate change in f. So notice that this df is going to be pretty close to this change of f. And actually, I hope you caught me here, because in fact, our picture is drawn correctly. What we're really looking at is the change of the output from this starting value, which was over here at R. So we're just moving flat, no change in Z would be R. So then we're moving up to S. So this would be where we see the differential df. Okay. Which is going to give us a fairly good approximation for the change of F. So now I just want to make a few notes about this work here. So first of all, on some of the notation. So I've been using dx and also delta x kind of interchangeably, and that is because they are just different names for the same thing. So a note on notation. So dx is equal to delta x. It's just equal to the change in x variable. And then similar story goes with dy or delta y. So that's just representing the change in y variable. So now the key point or takeaway is the following, is that we can approximate the change of f by using the differential df. And this approximation gets really good for small values of dx and dy. So this is fairly approximate for small values of dx and dy. So if we don't vary too much from our initial starting point, then using this differential, this tangent plane, to approximate our function is going to be pretty good. Awesome. All right, well, great work working through these notes. Please make sure you're continuing on to the examples and exercises that follow.